As discussed in the introduction, an excellent IB physicist should be aware of the course aims, appreciate the nature of physics and science more broadly, and know how to learn and how to inquire. The skills associated with inquiry have already been discussed and will be referred to once again in the internal assessment and extended essay chapters. In this chapter, you will find out about the 3 tools that physicists benefit most from: experimental techniques, technology, and mathematics. Read this chapter before embarking on your studies and continue to refer back to the skills addressed, as almost all elements will be required in any of the topics that follow. When preparing for external assessment, in particular Paper 1B, you may wish to attempt the practice questions that are located in the ebook. Tool 1. Experimental Techniques. Physics is about modeling the physical universe so that we can predict outcomes, but before we can develop models, we need to define quantities and measure them. To measure a quantity, we first need to invent a measuring device and define a unit. When measuring, we should try to be as accurate as possible, but we can never be exact. Measurements will always have uncertainties. This could be due to the instrument or the way we use it, or it might be that the quantity we are trying to measure is changing. Making observations. Before we can try to understand the universe, we have to observe it. Imagine you are a cave person looking up into the sky at night. You would see a lot of bright points scattered about, assuming it is not cloudy. The points are not the same, but how can you describe the differences between them? One of the main differences is that you have to move your head to see different examples. This might lead you to define their position. Occasionally, you might notice a star flashing, so would realize that there are also differences not associated with position, leading to the concept of time. If you shift your attention to the world around you, you will be able to make further close-range observations. Picking up rocks, you notice some are easy to pick up, while others are more difficult. Some are hot and some are cold, and different rocks are different colors. These observations are just the start. To be able to understand how these quantities are related, you need to measure them, and before that, you need to be able to count. Standard notation. In this course, we will use some numbers that are very big and some that are very small. 602 gazillion is a commonly used number, as is 0.0000160. To make life easier, we write these in standard form. This means that we write the numbers with only 1 digit to the left of the decimal place, and represent the number of zeros with powers of 10. So, that massive number is equal to 6.02 times 10 to the 23. Decimal place must be shifted right 23 places. And that number there is equal to 1.60 times 10 to the negative 19. Decimal place must be shifted left 19 places. A number's order of magnitude is the closest whole power of 10. 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the 1, 10 to the 2, and so on are all orders of magnitude. Exercise. Question 1. Write the following in standard form. A. 48,000. B. 0.000036. C. 14,500. D. 0.0000048. Measuring variables. We have seen that there are certain fundamental qualities that define our universe from which all other quantities can be derived or explained. These include position, time, and mass. Length and distance. Before we take any measurements, we need to define the quantity. The quantities that we use to define the position of different objects are length and distance. To measure distance, we need to make a scale, and to do that, we need 2 fixed points. We take our fixed points to be 2 points that never change position. For example, the ends of a stick. If everyone used the same stick, we will all end up with the same measurement. However, we cannot all use the same stick, so we make copies of the stick and assume that they are all the same. The problem is that sticks are not all the same length, so our unit of length is now based on one of the few things we know to be the same for everyone: the speed of light in a vacuum. Once we have defined the unit, in this case the meter, it is important that we all use it. or at least make it very clear if we are using a different one. There is more than one system of units, but the one used in this course is the Sistema International de Unitats, SI units. Here are some examples of distances measured in meters. Distance from the Earth to the Sun is equal to 1.5 times 10 to the 11 meters. Diameter of a grain of sand is equal to 2 times 10 to the negative 4 meters. The distance to the nearest star is equal to 4 times 10 to the 16 meters. Radius of the Earth is equal to 6.378 times 10 to the 6 meters. Time. When something happens, we call it an event. To distinguish between different events, we use time. The time between two events is measured by comparing to some fixed value, the second. Time is also a fundamental quantity. Some examples of times. Times between beats of a human heart, 1 second. Time for the moon to go around the Earth, 1 month. Time for the Earth to go around the Sun, 1 year. Mass. If we pick up different objects, we'll find another difference. Some objects are easy to lift up, and others are difficult. This seems to be related to how much matter the objects consist of. To quantify this, we define mass by comparing different objects to the standard kilogram. Some examples of mass. Approximate mass of a human is 75 kilograms. Mass of the Earth is 5.97 times 10 to the 24 kilograms. Mass of the Sun is equal to 1.98 times 10 to the 30 kilograms. Area and volume. The two-dimensional space taken up by an object is defined by the area, and the three-dimensional space is volume. Area is measured in square meters, and the volume is measured in cubic meters. Area and volume are not fundamental units, since they can be split into smaller units, m times m or m times m times m. We call units like these derived units. A list of useful area and volume equations is located in your data booklet. Density. By measuring the mass and volume of many different objects, we find that if the objects are made of the same material, the ratio of mass over volume is the same. This quantity is called the density. The unit of density is kilograms per meters cubed. This is another derived unit. Examples include density of water, which is equal to 1.0 times 10 to the 3 kilograms per meters cubed. Density of air is equal to 1.2 kilograms per meters cubed. Density of gold, 1.93 times 10 to the 4 kilograms per meters cubed. Displacement. So far, all that we have modeled is the position of objects and when events take place. But what if something moves from one place to another? To describe the movement of a body, we define the quantity displacement. This is the distance moved in a particular direction. The unit of displacement is the same as length, the meter. Referring to the map in Figure 2, if you move from B to C, your displacement will be 5 kilometers north. If you move from A to B, your displacement will be 4 kilometers west. Angle. When two straight lines join, an angle is formed. The size of the angle can be increased by rotating one of the lines around the point where they join, the vertex, as shown in Figure 3. To measure angles, we often use degrees. Taking the full circle to be 360 degrees is very convenient because 360 has many whole number factors it can easily be divided by. Examples 4, 6, and 8. However, it is an arbitrary unit not related to the circle itself. If the angle is increased by rotating line A, the arc lengths will also increase. So for this circle, we could use the arc length as a measure of angle. The problem is that if we take a bigger circle, then the arc length will be the same angle for the same angle will be greater. We therefore define the angle by using the ratio S over R, which will be the same for all circles. This unit is the radian. Summary. Tool 1. Experimental techniques. So far, you will have become familiar with a range of experimental techniques, including measurements of length, time, mass, volume, angle. These tools are prescribed in your subject guide. These are others still to come throughout the textbook. These include measurements of force, A2, temperature, B1, electrical current, B5, electric potential difference, B5, sound intensity, C2, and light intensity, C2. You should also be aware of how to recognize and address safety, ethical, and environmental issues. Try to spot these throughout the book, such as the risks of high-temperature fluids, B3, or ionizing radiation, E3, or the environmental impact of using electricity, B5, or water, C2, for experimentation. Tool 2. Technology. Technology and physics are closely linked. Technology enables the advancement of physics, while the pursuit of scientific understanding stimulates improvements in technology. The fields impacted are as wide-ranging as communication, medicine, and environmental sustainability. Every measurement requires an instrument, which is in itself inherently technological. Technology facilitates collaboration, which is to the benefit of international teams of scientists and IB physicists alike. Technology makes the processes carried out by physicists much faster, for example, when collecting data or performing calculations. Humans can sense light intensity, temperature, sounds, smells, tastes, and applied pressure. How might technology replicate or improve upon these senses? What else does technology enable us to measure? A model is a representation of reality. It can be as concise as a single word. Example, the brain is like a computer. Or an equation. Example, speed is the ratio of distance traveled to time taken. Technology supports physicists in forming new models during exploratory experimental work. Example, by making it easy to compare the fit of a range of mathematical relationships, and in creating simulations that enable experimentation without need for a lab. Summary. Tool 2. Technology. Technology can be used to good effect in physics. The Tool 3 Mathematics section of this chapter will reveal that technology can be used to display graphs about representing data. In the remainder of the textbook, you can expect to learn about using sensors, A2, B1, B3, C1, C4, models and simulations of generation of data, B2, C4, spreadsheets for manipulation of data, B5, computer modeling for the processing data, C1, image analysis of motion, C5, E1, databases for data extraction, C5, E5, video analysis of motion, E3. Tool 3. Mathematics. When counting apples, we can say there are exactly 6 apples, but if we measure the length of the piece of paper, we cannot say it is exactly 21 centimeters wide. All measurements have an associated uncertainty, and it is important that this is also quoted with the value. Uncertainties cannot be avoided, but by carefully using accurate instruments, they can be minimized. Physics is all about relationships between different quantities. If the uncertainties in measurement are too big, then relationships are difficult to identify. Throughout the practical part of this course, you will be trying to find out what causes the uncertainties in your measurements. Sometimes you'll be able to reduce them, and at other times not. It is quite alright to have big uncertainties, but completely unacceptable to manipulate data so that the numbers appear to fit a predicted relationship. Summary of SI units. The SI system of units is the set of units that are internationally agreed to be used in science. It is still okay to use other systems in everyday life, miles, pounds, Fahrenheit, but in science we must always use SI. There are 7 fundamental or base quantities. Base quantity, length. Quantity symbol, X or L. Unit, meter. Unit symbol, M. Base quantity, mass. Quantity symbol, M. Unit, kilogram. Unit symbol, kg. Base quantity, time. Quantity symbol, T. Unit, second. unit symbol S. Base quantity, electric current. Quantity symbol I. Unit ampere. Unit symbol A. Base quantity, thermodynamic temperature. Quantity symbol T. Unit Kelvin. Unit symbol K. Base quantity, amount of substance. Quantity symbol N. Unit mole. Unit symbol MOL. Base quantity, luminous intensity. Quantity symbol I. Unit candela. Unit symbol CD. All other SI units are derived units. These are based on the fundamental units and will be introduced and defined where relevant. So far, we have come across just 3. Derived quantity, area. Symbol, meters squared. Base units, m times m. Derived quantity, volume. Symbol, m cubed. Base units, m times m times m. Derived quantity, density. Symbol, kilograms per meters cubed. Base units, kilograms divided by meters times meters times meters. By breaking down the units of derived quantities into base quantity units, it is possible to check whether an equation could be correct. This technique is an informal version of dimensional analysis, in which the powers of quantities are compared on either side of an equation. Note, however, that dimensional analysis provides no insights into the constant of proportionality. Processing uncertainties. The SI system of units is defined so that we all use the same sized units when building our models of the physical world. However, before we can understand the relationship between different quantities, we must measure how big they are. To make measurements, we use a variety of instruments. To measure length, we can use a ruler, and to measure time, a clock. If our findings are to be trusted, then our measurements must be accurate, and the accuracy of our measurement depends on the instrument used and how we use it. Consider the following examples. Reducing errors. To reduce random errors, you can repeat your measurements. If the uncertainty is truly random, your measurements will lie either side of the true reading, and the mean of these values will be close to the actual value. To reduce a systematic error, you need to find out what is causing it and correct your measurements accordingly. A systematic error is not easy to spot by looking at the measurements, but is sometimes apparent when you look at the graph of your results or the final calculated value. Adding uncertainties. If 2 values are added together, then the uncertainties also add. For example, if we measure 2 lengths, L1 equals 5.0 plus or minus 0.1 centimeters, and L2 equals 6.5 plus or minus 0.1 centimeters, then the maximum value of L1 is 5.1 and the maximum value of L2 is 6.6. So the maximum value of L1 plus L2 is equal to 11.7 centimeters. Similarly, the minimum value is 11.3 centimeters. We can therefore say that L1 plus L2 is equal to 11.5 plus or minus 0.2 centimeters. If y equals a plus or minus b, then delta y equals delta a plus delta b. If you multiply a value by a constant, then the uncertainty is also multiplied by the same number. So 2L1 equals 10 plus or minus 0.2 centimeters, and half L1 is equal to 2.5 plus or minus 0.05 centimeters. Example of measurements and uncertainties. Let us consider an experiment to measure the mass and volume of a piece of modeling clay. To measure mass, we can use a top pan balance. So we take a lump of clay and weigh it. The result is 24.8 grams. We can repeat this measurement many times and get the same answer. There is no variation in the mass, so the uncertainty in this experiment is the same as the uncertainty in the scale. The smallest division on the balance is 0.1 grams, so the uncertainty is plus or minus 0.1 grams. So, mass is equal to 24.8 plus or minus 0.1 grams. To measure the volume of the modeling clay, we first need to mold it into a uniform shape. Let us roll it into a sphere. To measure the volume of the sphere, we measure its diameter, from which we can calculate its radius. Volume equals 4 pi r cubed divided by 3. Making an exact sphere out of the modeling clay is not easy. If we do it many times, we will get different shaped balls with different diameters. So let us try rolling the ball 5 times and measuring the diameter each time with a ruler. Using the ruler, we can only judge the diameter to the nearest millimeter, so we can say that the diameter is 3.5 plus or minus 0.1 centimeters. It is actually even worse than this, since we also have to line up the 0 at the other end, so 3.5 plus or minus 0.2 might be a more reasonable estimate. If we turn the ball around, we get the same value for d. If we squash the ball and make a new one, we might still get a value of 3.5 plus or minus 2 centimeters. This is not because the ball is a perfect sphere every time, but because our method of measurement is not sensitive enough to measure the difference. Let us now try measuring the ball with a vernier caliper. The vernier caliper can measure to the nearest 0.002 centimeters. Repeating measurements of the diameter of the same lump of modeling clay might give us the result in Table 1. The reason these measurements are not all the same is because the ball is not perfectly uniform and, if made several times, will not be exactly the same. We can see that there is a spread of data from 3.400 centimeters to 3.570 centimeters, with most lying around the middle. This can be shown on a graph, but first we need to group the values as in Table 2. Table 2 is here. Distribution of measurements. Even with this small sample of measurements, we can see in Figure 9 that there is a spread of data. Some measurements are too big and some too small, but most are in the middle. With a much larger sample, the shape would be closer to a normal distribution, as in Figure 10. The mean. At this stage, you may be wondering what the point of trying to measure something that does not have a definite value. Well, we are trying to find the volume of the modeling clay using the formula V equals 4 pi r cubed over 3. This is the formula for the volume of a perfect sphere. The problem is we cannot make a perfect sphere. It is probably more like the shape of an egg, so depending on which way we measure it, sometimes the diameter will be too big and sometimes too small. It is, however, just as likely to be too big as too small. So if we take the mean of all our measurements, we should be close to the perfect sphere value, which will give us the correct volume of the modeling clay. The mean or average is found by adding all the values and dividing by the number of values. In this case, the mean is equal to 3.537 centimeters. This is the same as the peak in the distribution. We can check this by measuring the volume in another way. For example, sinking it in water and measuring the volume displaced. Using this method gives a volume equal to 23 centimeters cubed. Rearranging the formula gives R equals the root of 3V over 4 pi. Substituting for V gives D equals 3.53 centimeters, which is fairly close to the mean. Calculating the mean reduces the random error in our measurement. There is a very nice example of this that you might like to try. Fill a jar with jelly beans and get your classmates to guess how many there are. Assuming they really try to make an estimate rather than randomly saying a number, the guesses are just as likely to be too high as too low. So, if you collect all the data, you find the average value. It should be quite close to the actual number of beans. Knowing the mean of data enables a calculation of the standard deviation to be performed. Standard deviation gives an idea of the spread of the data. Small samples. You will be collecting a lot of different types of data throughout the course, but you will not often have the time to repeat your measurements enough to get a normal distribution. With only 4 values, the uncertainty is not reduced significantly by taking the mean, so half the range of values is used instead. This often gives a slightly exaggerated value for the uncertainty. For the example above, it would be plus or minus 0.1 centimeters, but it is an approach accepted by the IB. Relationships. In physics, we are very interested in the relationships between two quantities, for example, the distance traveled by a ball and the time taken. To understand how we represent relationships by equations and graphs, let us consider a simple relationship regarding fruit. Linear relationships. Let us imagine that all apples have the same mass, 100 grams. To find the relationship between number of apples and their mass, we would need to measure the mass of different numbers of apples. These results could be put into a table, as in Table 3. In this example, we can clearly see that the mass of the apples increases by the same amount every time we add an apple. We say that the mass of apples is proportional to the number. If we draw a graph of mass versus number, we get a straight line passing through the origin, as in Figure 11. The gradient of this line is given by delta y over delta x, which is equal to 100 grams per apple. The fact that the line is straight and passing through the origin can be used to test if two quantities are proportional to each other. The equation of the line can be used to calculate the mass of any given number of apples. This is a simple example of what we will spend a lot of time doing in this course. To make things a little more complicated, let us consider apples in a basket with mass of 500 grams. The table of masses is shown in Table 4. The slope in Figure 12 is still 100 grams per apple, indicating that each apple still has the mass of 100 grams, but the intercept is no longer 0, 0. We say that the mass is linearly related to the number of apples, but they are not directly proportional. The equation of this line is y equals mx plus c, where m is the gradient and c is the intercept on the y-axis. The equation in this case is therefore y equals 100x plus 500. Finding the equation that relates two quantities can be useful for interpolation and extrapolation. Both techniques involve inserting a value for one of the quantities into the equation to find the corresponding value of the other. Interpolation can be performed with good confidence, as it is done within the range of collected data. Extrapolation is more risky as the values are beyond the range of collected data. You are making prediction. Nonlinear relationships. Now let us consider the relationship between radius and the area of circles of paper, as shown in Figure 13 on the following page. The results are recorded in Table 5. If we now graph the area versus radius, we get the graph shown in Figure 14. This is not a straight line, so we cannot deduce that the area is linearly related to radius. However, you may know that the area of a circle is given by a equals pi r squared, which would mean that a is proportional to r squared. To test this, we can calculate r squared and plot a graph of area versus r squared. The calculations are shown in Table 6. This time, the graph is linear, confirming that the area is indeed proportional to the radius squared. The gradient of the line is 3.1, which is pi to two significant figures. So the equation of the line is area equals pi r squared, as expected. Using logs can be useful in your practical work. In the previous exercise, we knew that area equals pi r squared, but if we had not known this, we could have found the relationship by plotting a log graph. Let us pretend that we did not know the relationship between a and r, or only that they were related. So it could be a equals kr squared, or a equals kr cubed, or even a equals k root r. We can write all of these in the form a equals kr to the power of n. Now if we take logs of both sides of this equation, we get log a equals log kr to the power of n, which is equal to log k plus n log r. This is of the form y equals mx plus c, where log a is y and log r is x. So if we plot log a versus log r, we should get a straight line with the gradient n and intercept log k. This is all quite easy to do using a spreadsheet, resulting in Table 7 and the graph in Figure 16. This has gradient equals 2 and intercept equals 0.5. So if we compare it to the equation of the line, log a equals log k plus n log r, we can deduce that n equals 2 and log k equals 0.5. The inverse of log k is 10 to the k, so k is equal to 10 to 0.5, which is equal to 3.16, which is quite close to pi. Substituting into our original equation, a equals k r to the power of n, we get a equals pi r squared. Relationship between the diameter of a modeling clay ball and its mass. So far, we have only measured the diameter and mass of one ball of modeling clay. If we want to know the relationship between the diameter and mass, we should measure many balls of different sizes. This is limited by the amount of modeling clay we have, but should be from the smallest ball we can reasonably measure up to the biggest ball we can make. In Table 9, the uncertainty in diameter d is given as 0.002 centimeters. This is the uncertainty in the vernier caliper. The actual uncertainty in diameter is more than this, as is revealed by the spread of data, which you can see in the first row, which ranges from 1.280 to 1.430, a difference of 0.150 centimeters. Because there are only 4 different measurements, we can use the approximate method using delta d equals delta max minus delta min divided by 2. This gives an uncertainty in the first measurement of plus or minus 0.08 centimeters. Table 10 includes the uncertainties and the mean. Now, to reveal the relationship between the mass m and diameter d, we can draw a graph of m versus d, as shown in Figure 17. However, since the values of m and d have uncertainties, we do not plot them as points, but as lines. The length of the lines equals the uncertainty in the measurements. These are called uncertainty bars. The curve is quite a nice fit, but very difficult to analyze. It would be more convenient if we could manipulate the data to get a straight line. This is called linearizing. To do this, we must try to deduce the relationship using physical theory, and then test the relationship by drawing a graph. In this case, we know that density, rho equals mass over volume, and the volume of a sphere equals 4 pi r cubed over 3, where r is the radius. So, rho equals 3m over 4 pi r cubed. Rearranging this equation gives r cubed equals 3m over 4 pi rho. But r equals d over 2, so d cubed over 8 equals 3m over 4 pi rho. Delta d cubed equals 6m over pi rho. Since 6 over pi rho is a constant, this means that d cubed is proportional to m. So a graph of d cubed versus m should be a straight line with the gradient 6 over pi rho. To plot this graph, we need to find d cubed and its uncertainty. The uncertainty can be found by calculating the difference between the maximum and minimum values of d cubed and dividing by q. D max cubed minus d min cubed over 2. This has been done in Table 11. Looking at the line in Figure 18, we can see that due to random errors in the data, the points are not exactly on the line, but close enough. What we expect to see is the line touching all of the error bars, which is the case here. The error bars should reflect the random scatter of data. In this case, they are slightly bigger, which is probably due to the approximate way that they have been calculated. Notice how the points furthest from the lines have the biggest errors. According to the formula, d cubed should be directly proportional to m. The line should therefore pass through the origin. Here we can see that the y-intercept is negative 0.3 centimeters cubed, which is quite close to the origin and is probably just due to the random errors in D. If the intercept had been more significant, then it might have been due to a systematic error in mass. For example, if the balance had not been zeroed properly, and instead of displaying 0 with no mass on the pan, it read 0.5 grams, then each mass measurement would be 0.5 grams too big. The resulting graph would be as in figure 19. A systematic error in the diameter would not be so easy to see. Since diameter is cubed, adding a constant value to each diameter would cause the line to become curved. Outliers. Sometimes a mistake is made in one of the measurements. This is quite difficult to spot in a table, but will often lead to an outlier on the graph. For example, one of the measurements in table 12 is incorrect. This is revealed in the graph of figure 20. When you find an outlier, you will need to do some detective work to try to find out why the point is not closer to the line. Taking a look at the raw data sometimes reveals that one of the measurements was incorrect. This can then be removed and the line plotted again. However, you cannot simply leave out the point because it does not fit. The sudden decrease in the level of ozone over the Antarctic was originally left out of the data since it was an outlier. Later investigation of this outlier led to a significant discovery. Uncertainty in the gradient. The general equation of a straight line graph passing through the origin is y equals mx. In this case, the equation of the line is d cubed equals 6m over pi rho, where d cubed is y and m is x, and the gradient is 6 over pi rho. You can see that the unit of the gradient is centimeters cubed per gram. This is consistent with it representing 6 over pi rho. From the graph, we can see that the gradient is 1.797 centimeters cubed per gram, which is equal to 6 over pi rho. So rho is equal to 6 over 1.797 pi. 6 over 1.797 pi is equal to 1.063 grams per centimeters cubed. But what is the uncertainty of this value? There are several ways to estimate the uncertainty in a gradient. One of them is to draw the steepest and least steep lines through the error bars as shown in figure 21. This gives a maximum gradient of 1.856 centimeters cubed per gram, and minimum gradient is equal to 1.746 centimeters cubed per gram. So, uncertainty in the gradient is 1.856 minus 1.746 divided by 2, which equals 0.06 centimeters cubed per gram. Note that the program used to draw the graph, LogoPro, gives an uncertainty in the gradient of plus or minus 0.03 centimeters cubed per gram. This is a more correct value, but the steepest and least steep lines method is accepted in IB assessments. The steepest and least steep gradients gives maximum and minimum values for the density max, which equals 6 over 1.746 pi, which equals 1.094 grams per centimeters cubed. Rho min, which equals 6 over 1.856 pi, which equals 1.029 grams per centimeters cubed. So the uncertainty is 1.094 minus 1.029 divided by 2, which equals 0.03 grams per centimeters cubed. The density can now be written as 1.06 plus or minus 0.03 grams per centimeters cubed. Fractional uncertainties. So far, we have dealt with uncertainty as plus or minus delta x. This is called the absolute uncertainty in the value. Uncertainties can also be expressed as fractions. This has some advantages when processing data. In the previous example, we measured the diameter of modeling clay balls, then cubed this value in order to linearize the data. To make the sum simpler, let us consider the slightly bigger ball with a diameter of 10 plus or minus 1 centimeter. So the measured value d equals 10 centimeters, and the absolute uncertainty delta d is equal to 1 centimeter. The fractional uncertainty of delta d over d is equal to 1 over 10, which equals to 0.1, or expressed as a percentage, 10%. During the processing of the data, we found d cubed equals 1,000 centimeters cubed. The uncertainty in this value is not the same as in d. To find the uncertainty in d cubed, we need to know the biggest and smallest possible values of d cubed. These we can calculate by adding and subtracting the absolute uncertainty. Maximum d cubed equals 10 plus 1 cubed, which equals 1331 centimeters cubed. Minimum d cubed equals 10 minus 1 cubed, which equals 729 centimeters cubed. So the range of values is 1,331 minus 729, which equals 602 centimeters cubed. So the uncertainty is therefore plus or minus 301 centimeters cubed, which rounded down to one significant figure gives us plus or minus 300 centimeters cubed. This is not the same as delta d cubed, which would be 1 centimeters cubed. The fractional uncertainty in d3 is equal to 300 over 1,000, which equals 0.3. This is the same as 3 times the fractional uncertainty in d. This leads to an alternative way of finding uncertainties when raising data to the power of 3. If delta x over x is the fractional uncertainty in x, then the fractional uncertainty in x cubed is equal to 3 delta x over x. More generally, if delta x over x is the fractional uncertainty in x, then the fractional uncertainty in x to the power of n is equal to n delta x over x. So if you square the value, the fractional uncertainty is 2 times bigger. Another way of writing this would be that if delta x over x is the fractional uncertainty in x, then the fractional uncertainty in x squared would be equal to delta x over x plus delta x over x. This can be extended to any multiplication. So if delta x over x is the fractional uncertainty in x, and delta y over y is the fractional uncertainty in y, then the fractional uncertainty in xy is equal to delta x over x plus delta y over y. It seems strange, but when dividing, the fractional uncertainties also add. So if delta x over x is the fractional uncertainty in x, and delta y over y is the fractional uncertainty in y, then the fractional uncertainty in x over y equals delta x plus delta y over y. If you divide a quantity by a constant with no uncertainty, then the fractional uncertainty remains the same. This is all summarized in the data booklet as, if y equals ab over c, then delta y over y equals delta a over a plus delta b over b plus delta c over c. And if y equals a to the power of n, then delta y over y equals n times delta a over a. Example, if the length of the side of a cube is quoted as 5 plus or minus 0.01 meters, what are its volume and the uncertainty in the volume? Fractional uncertainty in length is 0.01 over 5, which equals 0.002. Volume equals 5 cubed, which equals 125 meters cubed. The absolute uncertainty. When a quantity is cubed, the fractional uncertainty is 3 times bigger, so the fractional uncertainty in volume equals 0.002 times 3, which equals 0.006. The absolute uncertainty is therefore 0.006 times 125, which equals 0.75, approximately 1. So the volume is 125 plus or minus 1 meter cubed.